Yeah, so first looking at the naive computation. So we have an example here with Rhabarber and Barbarei. And you see here, if you want to compute the edit distance here, then you see that the last letters, the last symbols do not match. Yeah? So R and I, that is a mismatch. So we are in this last case here where we have to do something. So this is 1 plus the minimum of, well, what? Well, the question is, we could substitute each other and just move forward backwards actually with both sequences. So this is the first case here in this minimum. Or we could keep R and try to match R to E. Yeah? So this is this case here. So we delete I here from the second sequence, but keep the first sequence, so to say. Yeah? This is this second step here, or the second case. And then finally we have the possibility to keep I here and move forward in this direction with the first sequence, so deleting R actually, and try to match I to E, which is the predecessor of R in Q in the first sequence. This is, this is the last case here. Yeah, and since we don't know which is the minimum, we have to move forward, and you see here that in each branch we have potentially, well, if it's a match, then we are good, but potentially we have in all of the branches again 3 branches. So in each recursive call we may have in the worst case 3 calls, and the question is, how deep can that be? Well, for sequences of length n and m, this obviously runs down to, well, we can delete either this one or this one here. Yeah? So this goes down to n plus m. Yeah? N is the number of symbols, or the length of the first sequence, and m is the length of the second sequence. Yeah? So in the worst case, we have obviously 3 recursive calls that we have to evaluate, and how deep is that? N plus m. So in the worst case, this goes down to a tree that has O of 3 to the power of n plus m nodes. Yeah? And we have to potentially evaluate all of them in order to compute the minimum here in the root of this tree. Yeah? And well, obviously computation complexity of O of 3 to the power of n plus m is not really acceptable. So that is for longer sequences, this is really hard. So yeah, we need to come up obviously with a better solution. And well, the better solution is if we analyze the whole thing, okay, we may have those many function calls for the sequences here, but many of those calls, if we look at it a little bit deeper here, appear several times. Yeah, so for example, this one here is the same like this one here, and you find and this one here, and so on and so on. Yeah, so you will find a lot of calls of those 3 to the power of n plus m calls that appear repeatedly. Actually, there are only m plus 1 times n plus 1 calls that are different, yeah, which is in O of m times n, obviously. Yeah, so and that looks much better than this one here. It still looks a little ugly, but much better than this one here. Yeah, so from those calls here we have in this naive solution here in this tree, only those many calls are really different. And the question is, can we not just do the necessary calls and somehow store the results so that we just have to look it up? Yeah, and that is actually a solution to do it much more efficiently than 3 to the power of n plus m. So we store the results of all calls, requiring, of course, in the worst case, m times n space. But then if we can somehow systematically evaluate all those m times n calls, m times n results, then we have a time complexity of m times n instead of 3 to the power of n plus m. Yeah? And this systematic evaluation can be done by the so-called dynamic programming approach, and we will see how that works on the next slides. But before we do that, just an illustration of the acceleration. So for examples of m and n equals 5, 50 or 500. So 5 times 5 is 25 instead of 3 to the power of 5 plus 5, which is 10, is already approximately 60,000, yeah, instead of 25. Yeah? Operations, and you see that so many operations here are just, or calls are just redundant. Yeah? 50 times 50, it's even better, of course. 2,500 operations need to be evaluated, and here or called, and here it's yeah, a number which I cannot really say, and the same holds true, of course, for 500 times 500, which is yeah, the difference is just ridiculously big. Yeah, so coming down from 3 to the power of n plus m to m times n is such a huge improvement that you are, of course, extremely happy, even if this this one is some kind of a quadratic appearance. Yeah, but of course you'll take it. Yeah, if you just look at the sheer numbers, the speed up is really ridiculously huge. So how can we do that? There's the dynamic programming scheme is typically as follows. We have, yeah, a matrix where the rows denotes the elements of Q, and the columns, the elements of Q, the rows, the elements of S. So S is here on the left hand side, and Q is on top. And then you try to find the alignment, and you use this calculation scheme. You start at the very last end typically, and then you use 3 different steps depending on whether there is a match or not. So, well, the easiest thing is the diagonal step. So you go from I from the bucket or from the position ij to I minus 1 j minus 1 if there is a substitution or a match at the current characters of qi and si in q and s. Yeah? So if the corresponding element of s and the corresponding element of q matches or just need to be substituted, you go from here to the next step, to the next position, which is I minus 1, j minus 1. Yeah? Then a horizontal step to the left here represents obviously a deletion of the current character in qi. Yeah? So you go with q, you go 1 step to the left, and with s you keep the position. Yeah? So that is a horizontal step, and a vertical step is vice versa. So this represents a deletion of s or an insertion of si into q, actually. Yeah? So you keep qi, but you delete si from s, which means you insert si into q. Yeah? So yeah, that's it actually, and those 3 different schemes are applied, and then we try to move through this matrix, n times m matrix. We try to start at the far right end, bottom end here, and try to find the optimal alignment path using these 3 calculation schemes. And here you see how that works. So you could, yeah, again, Rhabarber and Barbarei. So don't get confused with this symbol here. Just should tell you that this is the current position where you are, or left to this symbol here. That's the current position where you are. So the first thing is that you have to align R, or you compare R and I. So if you substitute it, or if it would be a match, you will go in this direction. If you delete R, you go in this direction, as you see here. If you insert I into Q or delete I from S, then you go in this direction. So this insert means insertion of the element from S into I into Q, or vice versa, the deletion of SI from S. Yeah, I think we called it deletion from S and deletion from Q, so don't get confused in that case. Yeah. So anyway, you see this here, and then, for example, or take this one here, for example, here, then you see, okay, now you're here, you're comparing E from Rhabarber with E from Barbarei, and then again you can take a substitution or a match, moving to this node here, or to this position in the matrix, and or you can delete the E from Barbarei, and then you are in this. This is a vertical step, or you can do a horizontal step by deleting this E here from Rhabarber. Yeah, and so you can think of this matrix here where you put Rhabarber on top here. So the symbols of Rhabarber denote the columns, and you put Barbarei here on the left hand side. So the column, the rows represent the symbols of Barbarei, the second sequence.